Hey everybody, checking in with you with our second video on binomial distributions. Today we're looking at the mean and standard deviation of binomial distributions. We're continuing with our example looking at the number of children with blood type O in a family of 5 from our last video. And you see we have a distribution of probabilities right here as well as our histogram to go with it as well. Now, if this were a chapter 1 topic, we'd be looking at the shape, the center, and the spread, or the SOCs of this distribution. Well, if we look at it, we can see the shape. It is very heavily skewed to the right, and we might be wondering why that is. Well, the idea is that because our probability of success is rather low, 25%, that most of our observations are here at the lower end, and where very few of our observations are at the higher end, and as we see, it is about 1.5% total probability that 4 or 5 of the children would have blood type O. We could also look at the center, and if we're looking for the center in this case, we'd be focusing ourselves on the median because this is a skewed distribution. And in order to find that, we'd be looking for where the sum of the probabilities adds up to 0.5, the cumulative probability. And when we look at that, it happens at when x equals 1. Now, if we wanted to find the mean of this distribution, we could rely on the fact that it is a discrete random variable, and we could use the sum of all the x times p's, and we would get 1.25. Happens to be pretty close to the median. And we could also use the variance rule, the sum of the x minus mean squared times probability, to get a variance of 0.9375 or a standard deviation of 0.968. Now, as we saw when we first were talking about discrete random variables, these formulas can get pretty tedious when there are a large number of x values. Good thing is that when we're looking at binomial distributions, there's actually some pretty neat shortcuts to finding the mean and variance of those values there. And those values are, the mean is just n times p, and the standard deviation is the square root of n times p times 1 minus p. In other words, the variance is n times p times 1 minus p. So we can go ahead and use those two formulas rather than having to rely on the more lengthy discrete random variables formulas. But we have to keep in mind that in order to use these, we have to establish that the distributions are binomial first. So let's look at an example. This is Mr. Bullard's 21 AP statistics students did the activity on page 340, which was just an activity looking at to determine whether the students could determine whether water was tap water or from bottled water. And it says if we assume the students in his class cannot tell tap water from bottled water, then each has a 1/3 chance of correctly identifying the different type of water by guessing. So we're going to refer to x as the number of students who correctly identify the cup containing the different type of water. So clearly this is a binomial distribution because all 4 conditions are met. I think we have that by now. So let's just jump right ahead to finding the mean and standard deviation of this distribution. Now, all we have to do is rely on our rule, as we just established on the previous slide, that the mean is just n times p, so n is 21, p is 1/3, so we have 7 as the expected number of students to guess correctly. So if we're saying 7 out of 21, that's 1/3, which makes sense. We could find the standard deviation using the rule we just established, the square root of n times p times 1 minus p. Multiply square root, we get 2.16, and again we always want to put our answer back into the context of the problem. So it says if this were repeated many times with groups of 21 students who were just guessing, the number of correct identifications would differ from 7 by about 2.16. Again, relying on the fact that the definition of standard deviation is the average deviation from the mean. Now, when we look at these binomial distributions, we usually want to make some inferences about them. But there's only one problem with that. Most of the time when we collect this data, it's actually done without replacement. But we have a little bit of a caveat to our independence check that will allow us to, even when we do not have replacement, identify distributions that are almost independent, and therefore the distributions will approximately be binomial. Now, what that caveat is that your sample size has to be less than 10 times the population size. That's referred to as the 10% condition. Now, it says in the bottom here, when taking SRS of size n from a population size capital N, so you see lowercase n for the sample size, capital N for the population size, we can use the binomial distribution to model the count of successes in the sample as long as little n is less than or equal to 1/10 times big N, which again is that the sample is less than or equal to 1/10 of the population. So if your sample size is 10 and the population is 50, well, now you have 20% of the population, and that's no good. That would be too large of a sample size, and therefore the probabilities are going to change too much. But if your sample size is 10 and the population size is 1,000, well, then you're clearly less than 10% of the population, and therefore you're not changing the probability in any significant manner, which is why we can say that it is still approximately independent. So that will allow us to use the binomial rules. Sometimes, however, it's interesting to note that binomial distributions will also approximate normally. And in order to check that, we have to make sure that we look at two things. We have to look at n times p, and we have to look at n times p. But why does it look approximately normal? Well, let's take a look at this example here. We have this situation where n equals 10 and p equals 0.8, and we see that this distribution is clearly skewed to the left. But if we increase the sample size to, say, 20, keeping the probability of success constant at 0.8, from the first to the second histogram here, we see that it's starting to look a little bit more symmetrical. And if we increase the sample size to 50, well, now we're looking at something that is very, very close to a normal distribution. That's why we can see that the binomial distribution can be approximated by the normal distribution as long as n gets large. Now the question obviously is, how large is large enough? Well, our rule of thumb is that if n times p is at least 10 and n times 1 minus p is at least 10, then that will allow you to say that the binomial distribution is approximately normal. And that means we can use things like the normal CDF and the inverse norm function on our calculator to approximate these values for the probabilities. But again, we have to make sure that we check that n times p is at least 10 and n times 1 minus p is at least 10. In other words, the expected number of successes and the expected number of failures are at least 10. All right, that's it for this lesson here. And next time we'll come in and we'll talk about geometric distributions. Have a good day.